Today we have a masonry pier design, and it's similar to a wall but a little bit more challenging because we don't really know if the steel has yielded, whereas in a wall the steel generally does yield. It really is dependent in this case on the axial load, and for this problem we're going to assume a P factored of 175 kilonewtons. And like I said, there's four possibilities: either both upper and lower steel yields, or they don't yield at all, or the top yields only, or the bottom yields only. So for this problem, we're going to assume that that all the steel doesn't yield, and we'll see if that's justified when we finally solve the problem and just recheck that assumption. So let's just get right into this. Best way to explain it, I think. So first of all, you want to determine what the strains are in the top and bottom steel, and this distance here I should be giving is 95 millimeters from the top steel to the top of the section, and also it's 95 millimeters from here to the bottom of the section, 95. So let's start with the strain compatibilities. This neutral axis location C is unknown, and we're going to solve for it. So we have the neutral axis is to 0.03. What this distance is, which is C minus that, which is 95. C minus 95 is to strain in the steel prime. So strain in the steel prime is 0.003 times C minus 95 over C. And we do the same thing for strain the steel. We can say C is to 0.003 what this distance is from here to here, which is D minus C, and D is 390 minus 95. 390 minus 95. So that's 295 minus C is to the strain in the steel. Solving for strain in the steel, it's 0.03 times 295 minus C over C. And now we could write out the equations, the equation of equilibrium for this problem. So we have the factored load externally applied, P factored, is equal to the forces internally on the section, which are right here. The force in the masonry, plus the force in the steel prime, which is this top steel in compression, minus the force in the steel and in tension. So we can also write out what the forces are in the masonry, steel prime, and steel. We'll do that right now. We'll say force in the masonry is equal to the stress block, really, phi m x 0.85 f prime m b times a, and a is equal to C over C times 0.8. So A is C times 0.8. And the force in the steel prime, which is also compressive, is going to equal the phi of the steel, 0.5, times the area of the steel times the stress in the steel. But we don't know if it's yielded or not. We're assuming it isn't yielded, so it's going to be the strain in the steel prime, which is this, times the modulus of elasticity. That gives us stress, E times strain. So that's going to be 0.003 times C minus 95 over C times the E of the steel, which is 200,000. And we do the same for the strain and for the force in the steel in tension here. It's going to be phi of the steel, area of the steel, times this strain here, times E, 0.003, times 295 minus C over C times E of the steel. So let's just put it all together into one equation. So P factored, that's 175,000. That's equal to force in the masonry, which is phi of the masonry, 0.6 times 1 times 0.85, 7.5, times the width of the section, which is 390, times 0.8 C, plus 0.85 times the area of steel, bottom or top, it's the same as 1,000. 2 times 500 millimeters squared. Each one of these is 500 millimeters squared, so 2 is 1,000. Times 0.003. So that's the phi of the steel, the area of steel, and then the E of the steel is 200,000. Times C. Well, we could actually note that these terms are the same, these are common, so we can put that in brackets and to say C minus 95 over C minus 295 minus C over C. And we could further simplify it, we could say that's 175,000 is 0.6, 0.85, 75, 390 times 0.8. That's 1,190 C. Plus this term, 0.85 times 1,000 times 0.003 times 200,000, which is 510, times 10 to the third, times C minus 95 minus this term. And I'll just leave it like that. I'll say it's C minus 95 over C minus 295 minus C over C in brackets. So we'll stop right there for today, and then tomorrow we'll solve this equation for C, and then check that these strains are indeed below 0.002, which is the yield strain. If it's above 0.002, then it means that we could substitute directly in a stress of 400 MPa, which is the yield stress of the material. So we'll do that, and then we'll carry on and give this pier a height and determine amplification effects. Alright, so let's stop right there for today then.